Thank you.
Okay. So once again, thanks for the kind introduction. I'm excited to be here and talk to you about our work. So I'll talk to you about Cutter, which is our tool that automates weak memory model meta-theory using automata. And I'll start by explaining what weak memory models are and why we care about them. So let's start with an example. Here I have two threads. I have a publisher thread and a subscriber thread, and two shared variables, data and flag, initially being 0. Now the publisher sets data to 42 and then sets the flag. And then if the flag is 1, the subscriber checks if the flag is 1 and then ensures that the data that it reads is equal to 42. So now the question is whether this assertion is ever violated. And if we think about this, naively in the beginning, we see that, if the subscriber here reads 1 for flag, then it should also see 42 for data, so that the program seems safe. But in practice, the answer to this question is that it depends. And whether the assertion is violated depends on the platform that we run this under, the compiler, the programming language, and so on. And just to give you some concrete examples, if we run this under sequential consistency, then this is safe. The assertion is not violated. Sequential consistency basically says that each thread executes its own instruction in order. So if the subscriber reads 1 for flag, it will also see 42 for data. A similar argument holds for TSO or x86. But if we run this program in a Raspberry Pi, in an ARM v8 machine, and we compile these accesses down to relaxed accesses, then we can in fact see 1 for the flag and then 0 for data, and same for C or C++11. And the reason is that in these two latter models, writes, for example, can be reordered. And if I reorder these two writes, the first thread can first write 1 for flag, and then the second thread can read 1 for flag and then read 0 for data. So answering these questions is not always easy, and this is where weak memory models come in. So a weak memory model, or a memory model in general, is something that specifies the values that a program can read. And so if, for example, we want to verify this program, right? If we want our verification results to make sense, then we also have to take into account the underlying weak memory model. So how do we do that? How do we model the semantics of concurrent programs under weak memory? One convenient way of doing so is by doing this declaratively. So we can define the semantics of a program P under a model M as a set of execution graphs G coming from the program, such that these graphs G are consistent according to the memory model. So this declarative semantics models the semantics of a concurrent program as a set of consistent execution graphs. Now, what does this mean? What is an execution graph coming from the program? Well, these graphs look somewhat like this. So because they're coming from the program, their nodes correspond to instructions. So this means write to data the value 42 corresponds to this instruction. Write to flag the value 1 corresponds to that instruction. And same for the reads here. This graph corresponds to the outcome where the assertion is violated. We read 1 for flag and 0 for data. I also have an initial node here that corresponds to the initializing writes to these two variables. I model both writes with a single event. So and these black edges are called PO edges, which stands for program order. These connect events of the same thread, and also the initializing writes to the first event of each thread. So this is how each of these execution graphs looks like. So for each of the scenarios I care about, I have a different graph. And these are kind of bare execution graphs. Now, the consistency predicate that defines consistency on execution graphs does so by defining different types of edges on these graphs that basically model some relations between the instructions. And just to give you a couple of examples, some standard relations, I'm also going to be using them, these relations in a second, is the RF relation, or reads from, which shows where reads are reading from. So this is reading 1 from this right here. The read of data is reading 0 from that right up there. And the CO relation, which stands for coherence. And this is a strict total order among same location writes. So here it orders the initial write to data with this write to data here, and the initial write to flag with this write to flag. So this declarative semantics basically says that if each model defines a bunch of relations on these graphs and then restricts the shape that these graphs can have. For example, one model might say that cycles that contain these 4 different types of edges are disallowed, or this relation needs to be reflexive, and so on. And the semantics is very convenient for defining different memory models. Now, during the past few years, there has been a very long line of work that tries to answer questions, memory model meta-theoretical questions, like, is a model A stronger than a model B? So for example, if I have that a graph G is consistent under A, does this imply that the same graph G is consistent under B? Or is a compilation scheme from a model A to a model B sound? Or is a given program transformation sound according to a given model? And so on. Now, these questions are not really easy to answer. And in fact, they have been proven quite error-prone. And I have just some testaments to that here. So, for example, the Java model is broken. Fixing the Java model. Compiler optimizations are invalid in C and C++. What we can do, how to fix them. Sequential consistency is defined in C and C++, and how is defined, how to fix it, and so on. So the point is that it's hard to define good models and models that satisfy the properties that we want, so that we're able to reason about them. And these usually require experts and months of work by experts and so on. So when we started this work, we tried to see if we can answer these questions in an automatic manner, so that this is less error prone. And since I'm giving this talk, you can imagine that the answer is yes. But I do not just want to convince you that we can do this. I also want to explain why and how we can do this. And by the way, if at any point you have any questions, just stop me. I'm not planning to use a full slide anyway, so we can make this an interactive talk. So the reason why we can answer questions like these in an automatic manner is because of this observation here. And the observation says that most models can be expressed as an irreflexivity constraint over some expression E. And this expression E is written in clean algebra with tests, or CAT. So what is clean algebra with tests? Well, it's basically regular expressions. So here I have the standard regular expression operators, and I have this R stands for some built-in relations. So an expression in CAT is either some standard regular expression or a test, T. And tests are either some built-in predicates, P, or true, or false, or disjunction, conjunction, complement. So using this very simple grammar in clean algebra with tests, we can express most weak memory models. And just to convince you about this, I'm going to give you a couple of examples. The exact definitions are not important, but I just want to show you that we can use this grammar to express the memory model predicates. So sequential consistency can be expressed as an irreflexivity constraint over this transitive closure. These are built-in relations. This R here, yes, this built-in relations. And for TSO, again, we have an irreflexivity of a transitive closure, where one of these relations is defined as this transitive closure here that also utilizes tests and so on. So why does this observation allow us to answer questions automatically? The reason is that we can reduce memory model queries to language inclusion, to a language inclusion problem, which is decidable under CAT. And what we show in the paper is that in order to prove a irreflexivity implication like this one here, we can, it suffices to show that B is included in A, which again is decidable in CAT. Now, if in case this was not clear, the questions that I had here, these questions are basically irreflexivity implications, right? So, for example, if I want to prove a program transformation sound, I have my original definition, and then I have my definition of the same model that employs the transformation, and I want to prove that, you know, the old definition applies the new one, the irreflexivity of the old one applies the irreflexivity of the new one, and the other way around, that the irreflexivity of the new one implies the irreflexivity of the old one. And so what we can do is reduce this to this language inclusion problem and answer all these kind of meta-theoretical questions. And in fact, this is what we've done. We have developed a tool that's called Cutter, which is basically a sound and automated way to answer memory model questions. And we can use Cutter in two different modes. The first one is as a theorem prover, as a prover mode, basically, which we use to reproduce a number of positive and negative literature results. The most interesting of which was the fact that we found that the proposed compilation scheme from C11 to power is broken. In reality, this took, again, like a lot of work from experts. This was a published paper and so on, and found a flaw in the standard. Cutter is able to prove to find a counterexample in the proposed compilation scheme of the standard in less than a minute. And the other mode at which we can use Cutter is this meta-programming mode, where basically we can use Cutter to spit out the code that state-of-the-art model checkers use for verification. I'm not going to talk about this in this talk, but just to give you a very brief idea, in the beginning I said that this declarative semantics is basically defines the semantics of a program under a set of consistent graphs. So state-of-the-art model checkers verify programs by enumerating this set of consistent graphs. And until now, for each different memory model, somebody had to write some routine that does the consistency check for each memory model. But now with Cutter, we can use Cutter as a meta-programming tool that spits out this code that can be used by model checkers to use consistency. So there's this manual procedure that was also error-prone is automated by Cutter. Now this is all the all the slides I have, and in the rest of the talk, I'd like to show you how the tool works and show you what kind of results we can prove. So let's start the examples. If this is not visible. So here I have, I declare 3 relations. I declare RF inverse, and MO. This MO is the same as the CO I had in the slides, orders, same location rates. And then I'm defining a couple of more relations. I define FR as RF inverse followed by MO. And then I also define 2 versions of echo. One is this transitive closure. The other one is this version here. It doesn't have a transitive closure. Again, the exact definitions are not important, but in general, in the weak memory literature, it is well known that these versions of echo are equivalent. So I'd like to prove that with Cutter. So basically, what I want to show is that irreflexivity of one implies irreflexivity of the other. So I want to show these 2 inclusions. Okay. Let me run Cutter on this example. So I run Cutter, and it tells me that the assertion that I'm trying to prove, actually this one does not hold, and it gives me a counterexample. So what is this counterexample? Cutter tries to prove the inclusion. So this is basically a word, this whole thing is a word that is accepted by the left-hand side, but not accepted by the right-hand side. And the counterexample that I get here is split into two parts, denoted by this arrow. The left-hand side of the arrow, so to speak, this is basically the point at which the left-hand side of the inclusion and the right-hand side of the inclusion diverge. So this is a transition that this echo 2 cannot take. And the part after the arrow is what else the left-hand side needs to do in order to reach an accepting state. So let's take a look at this example. Here it says that the left-hand side can take an RF step from this RF part here. And then, due to the transitive closure, it can start an FR transition, the first step of which is an RF inverse. The right-hand side cannot do that because after this RF, it's basically in an accepting state, cannot do anything else. And this part is that the left-hand side needs to take an MO step in the end to reach an accepting state. So we get this counterexample, which seems reasonable in the beginning, but in fact, this is because Cutter doesn't know anything about the semantics of these relations, at least because these are relations that I have declared. Right, and in fact, it doesn't know that RF inverse is the inverse of RF. So this is basically the identity relation, and I need to tell it that if I am to proceed with this proof. So I can tell Cutter assume that RF and RF inverse is basically the ID, and then I can run Cutter again, and now I get a different counterexample, which now tells me that the left-hand side can take an RF step and then an MO step. Again, makes sense. The right-hand side cannot do that. It can only do an RF step. Then it's in an accepting state. It cannot do anything. By the way, these are tests. This empty test means true. So in this case, there are no actual tests, but this is what these brackets are. Now, this counterexample is because, again, Cutter doesn't know anything about the semantics of these relations. Now, in the beginning, if you remember, I showed that this RF goes from writes to reads. In a similar manner, the inverse goes from reads to writes, and MO connects same location writes. So in this counterexample, if the left-hand side takes an RF step, it goes from a write to a read, and then it shouldn't be able to take an MO step, because if an event is a read, it can also not be at the same time a write. So if we do an RF step, then we cannot actually do an MO step. But Cutter doesn't know anything about the domains and the codomains of these relations, so I have to tell it something about it. I can say assume that RF and MO do not compose. It's the empty relation, and since we're at it, I can also say that RF does not compose with itself, because I'll get to a read, and then I cannot do another RF step. And what else is there? MO with RF inverse does not compose. Again, I go to a write, then this guy starts from a read. So I give all this info to Cutter, I run it again, and now I get a different counterexample. And in this case, again, I get this counterexample because Cutter doesn't know that MO is transitive. So yes, indeed, the left-hand side can take a couple of MO steps, and the right-hand side can only take one, and then it can just take an RF step. But MO is transitive, so there's a transitive step that basically covers these two transitions here. And I have to tell that to Cutter. So I'd say that MO is transitive. Then I run it again, and now it manages to successfully prove what I wanted. So this was my first example. A couple of comments. How do these assumptions work? So these work as saturations on the right-hand side. So here, for example, when I say that MO followed by MO is an MO, then Cutter will take the right-hand side of each of these inclusions. And whenever the right-hand side can take a single MO step, it will also allow it to do a couple of MO steps. Right. So basically, most of these assumptions work as saturations on the right-hand side that allow it to do a couple of more steps, and also allow my proof to proceed. Now, in this example, I have had to declare quite a few things that are obvious to anyone that has done anything related to weak memory models. But this is because these relations that I declared are user-defined relations, so Cutter doesn't know anything about them. And to avoid having to do that every time, we've built in into Cutter a theory that basically provides RF and MO and FR and PO and relations like that, and some assumptions on these relations, like there are domains and there are codomains and some extra info. And if I use the built-in versions of RF, MO, and FR here and try to prove the same thing, then Cutter manages to prove it with no help whatsoever, because this built-in theory that it has, it already knows the things that I had to tell it. So this was my first example. My second example is...
Can I have a question? Sorry.
Yeah.
About this procedure that you mentioned for
saturation.
Yeah, saturation.
Yeah.
Is it complete?
Good point. It is complete. Certain saturations are complete, not all of them. We have this in the paper, but basically for like these simple things here, it is complete. If you want to do some compilation proof and your assumption is like your compilation scheme, as I'm going to show later, then it's not complete. Or if you have any totality constraints, it's not complete. It is sound always, but it's not always complete. And we have this classification in the paper.
Okay, thanks.
Right. So in the second example, in this about this completeness, then it is complete if you call cutterness. Like you have to write your assertion in a specific manner. But I'm going to show you what this is with this example here. So here I have a couple of definitions of the release acquire model. So the first definition is this one. The second definition is this one. So the first definition defines this transitive closure as HB, and then it defines RA like this. And basically the model says that this needs to be reflexive. The second definition defines a different HB, where instead of RF, it has RF external here. So basically, RF is decomposed into RF external or RF internal, depending on whether it connects events from different threads, in which case it's an RF external, or events belonging to the same thread, in which case it's an RF internal. Cutter knows about this decomposition. So instead of RF, it uses RFE, and then it also uses a different PO that it's basically a subset of this PO here. And the second definition requires that this RA2 relation be reflexive. So this is like proving a program transformation. Basically, if you want to allow a read followed by a write followed by a read in a different location to be reordered, then you have to show that your consistency predicate does not depend on something like that. So you exclude that part from PO here, and you have a different definition, and you want to prove that these are equivalent. And take my word for it that these two definitions are in fact equivalent. I'm just going to try and prove this with Cutter. So again, what I want to prove is this and this. And now I'm using the built-in versions of all these relations. So let's run Cutter. And if I run it again, I get a counterexample. And as you can see, the counterexample, the counterexample is an RF internal edge, which makes sense because the left-hand side can do this HB here, and from this HB, it can do this RF internal step. The right-hand side, RA2, cannot do the same because even if it takes this HB here, it can only do RF external. So this seems like, again, reasonable. the reason why we get this is because if I want to prove this, then our RA being equal to RA2 is a sufficient condition to prove it. But it's not necessary. Put differently, if I know that I know this, then this does not imply that this holds, right? And in more practical terms, the counterexample that I get here is not actually an irreflexivity counterexample, because it says that I start with the write, then I do an RF, and then I end with a read. If this is to end on the same event in an execution graph, I cannot have the same event being both a write and a read. So in fact, what I want to prove is something that looks more like this. That I need to tell Cutter that these paths, these counterexamples that it gives me, need to end on the same exact event. And to do this, I can use this different operator here. So this inclusion operator that basically tells Cutter to find paths that start and end with the same type of edge. Now, if I do this, I get rid of the previous counterexample, and now I get this final counterexample for this proof, which is that the left-hand side can take an arbitrary PO step, anything before PO, anything after, which is because in the right-hand side I can only do this PPO, so end with the write or start with the read. And this is because Cutter does not know that basically I only have two types of events, reads and writes. And if I tell it that I'm only interested in reads or writes, and there's nothing else, then it should be able to complete this. It manages to prove it. All right. And maybe one last thing here. Suppose that I do a different definition for RA. I use this HB here, and I define RA as HB or MOHB or FRHB. And again, I want to prove that RA is equal to RA3. And now let me call it in this way. That will give me only paths that start and end with the same kind of test. So I can try and prove this. And now if I call Cutter here, I should get some counterexamples. And let's see, so I get like PO and then FR, which makes sense for this left-hand side. I can take PO from this HB and then FR. In the right-hand side, in RA3, I can take a PO, but then nothing else. So why am I getting this counterexample? And the reason why is because RA is not actually the same as R3, but it's actually equal to a rotation of R3, of RA3. Right away, I have here MOHB. Here it's HBMO, and same here I have HBFR and FRHB. So I actually have to tell Cutter to also look for rotations. And then if I try to prove that, then Cutter manages to prove success. So in principle, the more general procedure that if I want to prove some irreflexivity application, then I have to use both this ID and this rotation in order to get this completeness result. Yes, and this was my second example. This is all I want to say about this one. And my last example is compilation proof, just to show you how Cutter can be used to do compilation proofs. So here, I'm including definitions of a couple of different files, of different memory models. So this is the definition of PSO. Basically, this needs to be acyclic. The exact definition is not important. I'm including the RC11 definition. This is a referred version of the C11 memory model that basically defines a bunch of relations. It's much more complicated than TSO, and then it dictates that this needs to be acyclic. This PSC relation here. And then if I want to prove compilation, this is the inclusion that I want to prove. I could also have used rotation there, but it's not necessary for this example, so I'm not going to do it. And now suppose that I run this and I try to prove that compiling from this referred version of C11 to TSO is sound. And if I do this, I get the counterexample again. And from all the counterexamples that I showed you, this, in contrast to the ones in the beginning where Cutter was missing some knowledge and so on, this one actually makes sense. And the reason why I get this is because I haven't provided Cutter with a compilation scheme. So just like in reality, where when I compile from, say, C11 to TSO, the compiler needs to insert fences and specific parts and so on, then similarly here in Cutter, I have to provide it with a compilation scheme in order for it to be able to prove this inclusion. And in fact, the counterexample that I get is precisely like this right PO read is precisely a particular reordering that a TSO model allows. And the compilation scheme from C11 to this TSO basically said that whenever you have a write followed by a read, then the compiler needs to insert a fence in between. This is exactly what I write here in the assumption. And then if I run Cutter like this, it is able to prove this compilation. Maybe I can make this just for SC reads and writes. But anyway, the point is that whenever we're trying to prove some compilation, we also have to provide the Cutter with a compilation scheme to be able to prove the inclusion that we want. And yeah, that's basically all I had. This was my last example. I present to you Cutter, which is a sound and automated way to answer memory model questions. And Cutter can be used in two different modes, to either in this prover mode that I just showed you, or it can be used as a meta-programming tool that generates consistency checkers for state-of-the-art model checkers. Hopefully it will soon be open source. We have the artifact up, but we haven't released it on GitHub yet. The paper is going to be presented in about a month in Popl. And yeah, that was the end of my talk. I'd be very happy to take your questions and feedback.
Yeah, thank you very much.
Yeah. Michalis, thank you for the talk. So as far as I remember, in your paper, you used the cutter for compilation from IMM to either power or ARM, but not other. Why is that?
Sorry, I didn't catch the full question. We used a Cutter for the compilation from IMM to which one?
I think it wasn't the whole step for some reason. Not IMM to TSO, ARM, and power.
I remember we definitely did IMM to ARM. Maybe we also did to TSO. Maybe you're right, it was not the full set. I do not think there was any particular reason why, apart from maybe time constraints, but I do not recall any problems or any reasons why we wouldn't be able to compile to prove compilation from IMM to power, especially since we did RC11 to power, if I recall correctly.
Yeah, I mean, IMM to power should be a bit more complicated, I think.
I don't doubt it, and from the ones that we tried, the power ones were the most complicated ones. So, for example, we had to do some rotations manually instead of using this rot operator that I showed you, because Cutter would take a lot of time. But I do not recall any specific issues when trying IMM to power, for example. I'll try it and let you know.
Okay, thank you.
Okay.
By the way, Do you have any plans on integrating kata to Kok?
For what?
Do you have any plans to integrating kata in Kok?
Not as of now, not really, but yeah.
Yeah, because here we have Andrei, who is working on something similar, and maybe we'll try to do something like that in Kok.
As a library, you mean?
Sorry?
As a library.
Yeah.
I see. Yeah, no, we haven't thought of that, I think. Now we're trying to work mostly, in this second direction, this generating consistency checks, because now we can generate consistency checks for, not for irreflexivity constraints, but for cyclistic constraints only. And we're trying to see how to best kind of generate consistency checks for irreflexivity constraints as well. But yeah, I haven't really thought of what else we can do in this this first prover mode.
Yeah, I mean, as far as I remember, Victor had us intern working on something similar a couple of years ago.
I see.
Are there any other questions? I have a couple of questions. So the first is about this generation of consistency checks. So can you maybe very briefly present how does it work? Like, do you generate some automaton or?
Yes. So we don't have a slide for this, but maybe I can show you the paper. Well, I think we have a couple of examples. So,
by the way, Michalis, one quick question, because I most likely have to turn off my internet in a second. Your kata tool, was it written in C++?
yes.
Thanks. So Andrei, probably there will be some way to call it from our framework as well.
Right. So basically, for consistency checks, you have two automata, and one automaton is the memory model. So this is the automaton for sequential consistency, right? You get RF, CO, PO, these are all accepting, and this is the FR step. And you also translate your execution graph. This should be store buffering. So write to X, read Y, write Y, read X. You translate your execution graph into an automaton as well, and then you run the product of the two things, of the two automata. And there's a naive way to do this, like do the product for every pair of states. Like the memory model one, you can start from the initial state, but for the execution graph, the naive way to do this is to start from every state of the graph and see if and have every state as accepting, because the graph doesn't have any accepting states. So you can take the automaton for the execution graph and try all possible states as both initial and accepting, run the product, and then if the product reaches an accepting state, then this is a violation. And this is the naive way to do this. The smarter way to do this is to decompose these relations into like their immediate counterparts. So you write PO as PO immediate plus, and CO as CO immediate plus, and so on. And then when you add a new event in the graph, check consistency starting from that state only, because you know that the graph before it was consistent, right? You just added a new event. So if there is any consistency violation, it needs to include this new event. And then you run the product from this new state, this new event that you added as initial and final state. And if you find a cycle in the graph, and your memory model automaton has passed through an accepting state, then this is a violation. And basically this is linear time instead of quadratic, or quadratic. You know, the trying every state would be linear in the size of the product. And this is how these consistency checks that the cutter spits out look like for GenMC. But you basically, like if your automaton has two states, like the one I showed before, state 0 and state 1, the memory model 1, you do a couple of recursive calls, and this is how the product construction looks like in C++.
Yeah, cool. But I think that is there any relation like of this? I think this problem is called like regular language reachability in graph or something like this. Like basically the problem is if you have a graph, you have some starting vertex, and then you want to find all the paths that satisfy some regular expression.
Okay.
Yeah.
I didn't know the formulation like that, but I assume that the complexity should be the same for like whatever solution this has, right?
Yeah. Yeah, cool. Yeah, I maybe just thought maybe there are some like other algorithms to do this, but I don't know.
For us, it's convenient in the sense that we have the automata ready, right? So like running the product is easy. It doesn't cost anything. This is why it's convenient.
Okay. Yeah, another question is that so you're using this Cape theory, like clean algebra of tests. Do you think what extensions of the theory could be useful for these tasks? Like, for example, this you had this like a transposition of derivations, like this RF minus -1, and I think there are some variations of the theory that has this operator in the clean algebra, like when it's one of the operations in the clean algebra, and it's also there are results that it is also it's still decidable and all that. So maybe there are other useful primitives.
So I do not know. I'm not an expert in cat and so on. The one assumption that I used in the demo, that RF followed by RF inverse is a subset of ID. This isn't. I think this is standard cat. So you know, this is included in the standard cat, like this old papers about decidability and completeness and so on. So these you know, these sort of things, like that something is empty and that something is included in the identity relation, these are standard, and you do not lose completeness. But I do not know if there is any other extension that, you know, could provide something useful while still maintaining decidability. If you're aware of any, let me know.
Yeah, I'll just send you
a
couple of papers. Yeah.
Thanks.
So are there other questions? Okay, I think we can finish then. So thank you for the talk.
Thanks a lot.
Yeah.
Thank you so much.
Bye, guys.